seat available. Anyway, you see an empty spot, which is not mine, please take it. Thank you very much. Thank you to the Observatory for the kind invitation. Yes, it is true that we have been hosting cosmology workshop this week. It has been just finished. The workshop has been organized by the UCT Cosmology Group, led by Peter Dansby, who is here, Peter Dansby. And we have counted with several speakers from either Oslo or Cape Town, as well as people from Salamanca in Spain. That's why I'm here, because I'm, as we mentioned, I'm the president of the Society of Spanish Researchers in Southern Africa. We are 80 Spanish/South African/Southern African researchers working here and everywhere, but based in Southern Africa. And tonight, it is my great pleasure and a huge responsibility, of course, to introduce a colleague, a master somehow in many things that he knows and we do not, and even a friend. And he's the speaker tonight, of course, who is Jose Beltran, and who is based in Salamanca in Spain. It's a very nice place to visit, by the way. But what I want to mention here is that one of the oldest universities in Western Europe, but one of the first with an astronomy center. In those times, in Middle Ages, of course, astronomy was astrology. So people were looking at the skies for all the reasons, particularly physicians, soldiers, etc., to have the precise time to make, a physical operation on your body. And that was the reason of that astrology chair. So almost 600 years later, because that chair was created in the 16th century, mid-15th century, we've got a professor from Salamanca telling us not about how the sky is tonight, but how it's going to look like, not the sky, but the universe as a whole, in a few billion years. So don't panic, or maybe earlier, but be safe. Tonight you can enjoy the visit, say hi, or I love you, or I hate you to your family or friends, or whatever you've got at home. And in any case, it's a pleasure, as I said, to welcome Jose. I can read a biography, of course, by heart. I don't need the papers. I think you can go to Google his name and you will find it. Jose did his PhD in Madrid, finished in 2009, and then he did postdoctoral fellowships in 3 fantastic institutions: Geneva first, then Leuven, Louvain in Belgium, then Marseille in southern France. And probably at that time he was extremely exhausted of francophone countries like Switzerland and Belgium and France, and then he decided to return, call it that way, to Spain. And over there he has created his own group called GRACUS, General Relativity and Cosmology, at the University of Salamanca. So he has been able to put a lot of seeds in many different places and to enlighten and to help us in many different ways. I think it's the 5th or 6th time that he's here, visiting Cape Town and creating and forming and developing new generations. So I think, I don't have much to say. Just follow us in either our YouTube channel of Society of Spanish Researchers in Southern Africa. Thanks to the Ramon Areces Foundation, a Spanish foundation devoted to science outreach as well, and the Embassy and the Consulate of Spain in either Cape Town and Pretoria. In any case, enjoy, open your ears. I always say, and I think it's totally true, that when the mythological gods that we all believe in have some questions about how the universe behaves, they take the phone and phone us to know what the universe is going to do. So it doesn't matter which god, goddess, it, he, she you believe in, but probably when they try questions, it's how is this equation working? Is it stable, unstable, ghost, phantom, etc. So anyway, Jose, close is yours. Thank you very much. Thanks for this discussion. Sorry, I never come from my God, as far as I know. So, yeah. It's not working. Ah. Okay. So let me go through a very quick. See how we go now. Yes. So I think something like this. Yes, for the ancient civilizations, very before the civilization, but the civilization so it was very hard. I think it was first civilization. And then also, numbers, because they had some here. Because almost a very useful one. This one. So all these models that work on this, they work on also it starts with the record of and we go about and not much happened, and after that came the middle ages, right? Was the hero. So that's not a point of view. Just try to look at this. First, you can see this. So, when we have this other and we could say that you don't pay us people with the development of and that I understand. the knowledge these things together, realize that they're driven by the same force, this translation. So after that, from a relational point of view, this guy here, Francis Farmer, he was trying to comment, and there he showed how these very things in the sky were very for him with his arrow. And the delay by this time, till the early century, was those objects were with very accurate, so they couldn't were inside the galaxy for us. So this was the situation of the up here. And then we get to this modern relativistic cosmology space. And I'm calling it relativistic because in 1915, Einstein, you will know, some of you know at least, he developed his theory of improvement of Newton's law of gravitation. What? Some of you know that he was really a monster, and the way he got to develop the identity is mystery. And anyway, so he gave us a better scale for understanding Europe. And this theory was confirmed at Italy in 1990. And this was very important because it allowed for the construction of models for the universe. On the observational side, again, and this woman, she discovered a relation between the period and the luminosity of certain type of stars or satellites. And this was very important because we could use this object to calibrate distance. So with this relation, we could now measure with better precision distances to very far away. Okay. And one of the first things they did was to measure the distance to Andromeda. And then they realized that it wasn't an object of our galaxy. It was an object outside our galaxy. And this was the revolution, because that meant that our galaxy is not the entire universe. There are things out there. Okay? With this kind of measurements, now we could, they could start measuring distances to other objects, galaxies. And then in 1929, Hubble came out with the expansion of the universe. Essentially, what they did, they were these guys that I mentioned now, but essentially they could measure the velocity of those objects with respect to us and the distance. And then what they realized is that the farther away the object is, the faster they move away from it. Okay, and this is compatible with the idea that the universe is expanded as a whole, because then the farther away objects will move faster from us. Okay, I'm saying this because actually now it's known as Hubble law, this relation, but Liefeld did it before Hubble, and even vertical limit computed the value of the so-called average constant. But 1 year before, I think, he wrote the paper in French. In that paper, he computed the Hubble constant, but then the paper was translated into English, and then the Max himself said, you know, this value I got, use this data, I don't trust a lot, so let's remove this. And the value was removed from the English translation. Anyway, so then another interesting thing that happened in the in the 30s and the 30s is this dark matter thing. Is my so in the 30s, with the improvement of the cosmological observation, some guys, this big Swiss astronomer, realized that we know that galaxies they needed to see that there was really
you could see the telescope. And this was confirmed in the 70s by Vera Green with very instruments, so they had much better precision for that. And the essentially here within the center of the galaxy, the velocity of the star is to the galaxy. So you can count the stars that you see in the galaxy and then measure the velocity of the stars outside the galaxy, in the outer regions of the galaxy. And from the motion, you can infer the mass inside. You compare with the mass that you observe, and then they found that there is some missing. Okay. This is the so-called dark matter. Now we have many different proofs of the existence of dark matter. This might complain. That could be something else. We can talk about that later if you want. But I'm going to assume that dark matter is pretty real in the universe. And then since then, instruments have improved a lot. We have the Hubble telescope. We were able to measure the quasi-microwave background that I will explain in a minute with the cosy satellite that was launched in 1992. And we have many different measurements now, gravitational waves of many cosmological allow us to have a good understanding of the universe as a whole. I would like to mention this dark energy thing that was discovered in 98, and that I will talk about later. Just for Spaniards in the audience. Okay. So for you, this is very funny to see that Kobe is the same as the name of the mascot of the Olympic Games in Barcelona that happened in 1992 too. So I don't know if it's a coincidence, but okay, so with all these observations and following here, now we have a understanding of how our universe evolved and what our universe is doing and all of the properties of the universe. This is just the one of the evolution of the universe. It all started with Big Bang. Me, I have to be honest with you. This is just an equity. The period. Okay, so essentially we have theories, physical theories. Okay, theoretical understanding of the physical nature. After laws, very clear. So here we don't have the theory, so we don't really know what. What I'm going to now this 10 classes will be with respect to this period of time where we don't know. Okay. So maybe most of the interesting things, I wouldn't say that, happen in the very moments of the universe. And one of the interesting things that happened here is the so-called primordial nucleation effect. And this is when the lightest elements in the universe, hydrogen and helium, were created. So that moment, some of the elements okay. When the universe was from 50,000 years, the universe became light. And this is the light of the microwave background that we see today. And this is very important because it gives us information of how the universe was at this time. And so then, what happened essentially is that the matter in the universe, essentially, because that's what dominates the matter content of the universe, started from a very small distribution and then started collapse. And then the collapse of this matter will start creating galaxies and galaxy stars and all these kinds of objects. Okay? But what about where are we today? So the entire universe could be represented like this whole square, and each point here, I will make it a each point is essentially a cluster of donuts. Many. There is the global, which is our galaxy together with some other galaxy. It's like our new. And here we have the Milky Way. In one of the arms of the Milky Way, there is the solar system. And the third planet from the sun in the solar system is the Earth. This is what we need. Okay. You see that we are just a tiny, 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 tiny rock in the universe. And so if this doesn't increase your level of humbleness, I don't know what. Okay. So now let's start from here and see how all these different systems will happen. So let's start from our home system, or maybe not. Because now we live in this very peaceful place of the sun where it's burning hydrogen and emitting a lot of energy and light, is what it seems. So we happen to live in this kind of zone in the solar system. And this will last for another 5 billion years. After 5 billion years, the sun will run out of hydrogen, will not be able to maintain hydrogen fusion. And then what happens is that the core that will basically issue will collapse, and then the external layers of the sun will expand. And they will expand a lot. So they will engulf the Mercury and Venus for sure, probably the Earth, maybe up to Mars. So the habitable zone will be moved towards where Jupiter and Saturn will be. You might think that then we will need to move to these planets. Then at some point. Bad news is that, as the astronomers know, these planets are just huge balls of gas. So if you want to build a house, you don't have the soil where you could build it. So at most, we could build a station orbiting these planets, which will be that's an idea you want to push it. Okay. So this could be the McDonald's at the end of Long Street, and this will be the view from there, where the sun is 5 billion years older than the planet. Then at some point what will happen is that well, it will start burning helium, I think, but in the end it will become a white hole. Okay. Something very interesting is that not only the sun will expand, but when it expands, it will push all the planets towards outer because of the expansion. So this habitable zone will not be where the planets are now, much farther. Okay. Okay, so this is regarding the sun. Now let's look at another next domain that, as you know, because I just mentioned that, is Andromeda. And this is a picture of the sky where you can see Andromeda, right? Who can spot Andromeda there? Okay, this thing there. And remember that the first time that it was mentioned in the Wilson text was this year by this Persian astronomer. Okay, and it's very interesting because so it's an experimental object, but in principle you can see by making that. Of course, you need to go to a very dark place and you need to have good sight. I cannot see it, to be honest. But if you get decent binoculars, it's very easy. Okay, and it's not difficult to find. Actually, you can find it in the mountain. I think if you look north at the bottom, it's marked Andromeda. So yeah. Next is the sun. It's actually quite amazing. And when we're looking at it, think that this is something that is outside our galaxy. Okay? This is, for me, fascinating. And actually, it's a pretty big thing. It's just, it's pretty fast. So it's really big in the sky. But if you could see it, it's a quite big thing in the sky. Okay. Now, why I'm mentioning this? Because we could say that this is one of these nice networks that is quiet, doesn't pass around, and we are happy with it. Thing is that it's coming to visit us. So at some point, in a few billion years, it will be negative. And they will eventually, so they will collapse. Now, it depends that this is what it might sound, because galaxies are made of stars, and the space between stars is huge. So essentially, the stars will pass through without collapse. There is a lot of gas. That gas will collapse and will eat up the whole system. There are many interesting things that will happen. But essentially, what will happen is that they will pass, and then they will oscillate a bit, and in the end, they will form another galaxy. I discovered that in English, you have these two names for the eventual object. I don't even know how to pronounce it. Omega? I don't know. Anyways, so this is a view of the sky today. So this is our galaxy. This is something I guess most of you have seen at night in the sky. And this little thing here will be Andromeda. And this is ours. Okay, this is today. Now, if we wait a couple of billion years, then Andromeda will start being something very appreciable in the sky. So you won't need binoculars anymore. If any of you live the amount of years. The sun will still be the main sequence, so peacefully burning hydrogen. Then, in 3.5 billion years, Andromeda will be just a huge monster in the sky. It will be right there. We'll see. Maybe even a day. Sun still burning hydrogen. And then in 3.8 billion years, sun still is really burning hydrogen. And then the collapse will start. And then we will see how Andromeda starts disrupting all the stars and structures in the sky. So constellations will be famous. This will be in 3.9 billion years when the two stars are really meeting. And this is when the first encounter happens, because remember, it will go and then oscillate for a few times. Sun still is fully burning hydrogen. Okay. Now, in 4.6, the sun will already be a bigger red giant, and then Andromeda will start doing its thing. And 5.8, well, the sun will already be well gone. And then the two galaxies will form one single galaxy. This Andromeda. Okay. Some stars will be ejected, and the process is it's pretty complicated, but this is a big picture. Of course, the Earth will change a lot. So I get the same image, but by this time it will have been burned by the sun. So don't expect to see all. Okay. Okay, so this is the sun and our galaxy. If you want, homework. But now let's look at what happens for stars. And for this, let me show this diagram. I don't need to do with information, just the main branches. So it all starts with a molecular cloud that collapses because of gravity. And at some point, it will branch into 3 different branches depending on the mass of the original cloud. If it's not very massive, you will get the groundwork, so it will not produce a proper star, or you might get also an object like Jupiter that was about to be a star, is not. More interesting is when you can start burning hydrogen, and the mass is not very big, so you get a star like the sun, and then, as we discussed, it will spend roughly 10 billion years burning hydrogen, then it will go to this red giant phase, and then it will end its life with a planetary nebula and in a white dwarf that eventually will become a black dwarf. Nothing to do with the black star. And the cool thing is that this planetary nebula then can contribute to this molecular cloud and restart the whole process. And yeah, this is similar to this. What's it called? Of the spread. Who was it? Elton John was the singer, right? So if you know him, maybe you can suggest him to do a version with science. Because it's debugging, then instead of becoming a regular percent, it becomes a 30%. Okay. And the interesting thing is that this object is supernova. Maybe you know it's a huge explosion of the star when it cannot be gravitational collapse anymore. And the interesting thing is that these guys come from many elements, only helium, but also carbon, oxygen, nitrogen, all these kind of things. And this is what we are made of. So there is sentence, it's called that we are star dust, something like that. This is why. Okay. And when this happens, then there are two possible objects that you can form. Either a neutron star or a black hole. That depends on how massive this star was originally. A neutron star will become a pulsar, which is an interesting object, or a black hole. And the black hole will typically have a lot of matter around, so you will have an accretion disk. This accretion will fall into the black hole, and then we will be able to see, or sometimes we are able to see these guys by the emission in X-ray. Okay? They are black, so we cannot see them. Let me go a bit more into details for these guys because they're fascinating objects. They even made it in the movies. This guy has a name, yes. So you from, I don't know if all of you, but some of you certainly have seen this black hole. Also, interesting is that a few years ago, we got the first picture ever of a black hole. This is a natural picture. And the way they got this picture, to me, is it's amazing. They ran out of adjective for it. Because what they did, I'm going to give you a brief general explanation for it, but I encourage you to go and Google it and see how they did it, because it's really technologically amazing. So they took the telescopes around the globe, a few of them, and then they took some pictures of this region. Okay, I'm going to give you an analogy of what they did. So imagine you want to make a picture of Peter, and then I take my camera, and instead of using all the pixels, I use a bunch of them, a few, 10. With those 10 pixels, I should be able to reconstruct the whole face of Peter. Okay, that's what I did. But even more difficult, because the pixels were spread around the globe. So they were not even taken at the same time. So they had to synchronize the pictures with huge accuracy, okay? And put everything together and process the image and get the picture, okay? So, okay. So that's focus. Because something like so these black holes, despite being these fascinating objects, they are actually among the simplest objects in the universe. And what do I mean by this? Well, I mean that whatever black hole you have, you only need to tell me the mass of the black hole and how fast it spins. And that's all I need to describe everything about the black hole. Some of you may compare that you also need a charge. They could have an electric charge, but actually in the universe, black holes with a charge will quickly charge to be neutralized. So astrophysical black holes typically are without charge. So these two numbers are enough to describe this object. It's just two numbers. Do you know any other thing that you can describe with two numbers? It's amazing. And not only that, they are very, very physical, stable, and rigid objects. So take the Earth, okay? Put them on, okay? Then only the gravitational field of the moon on the Earth creates tides and deforms the air and many things. Now, take a black hole, put another black hole here, it will not get. So it will not be deformed by external gravitational field, okay? So they are pretty unique things. But as these two guys say, well, there might be some hope that they will remain forever, but not. Because then we know that the world is quantum, we have quantum mechanics, quantum mechanics here. But this guy, who knows who this guy is? I know. So this is Stephen Hawking, that suddenly passed away, isn't it? But he realized that through quantum mechanical processing, these objects will radiate. And by this radiation, they will evaporate. So of course, for very big objects, the radiation is very low, so the evaporation process is very low, and it will take many years. But actually, it's funny that if you have a very small black hole with a tiny mass, this emission will be green and this. So it won't be black anymore. It will be color. They are smaller. So yeah, these objects will eventually also die by emitting radiation. Now, I've been telling you about these single objects, but the thing is that stars like to live in couples. And this is right because I don't know if you know one. Penguins are considered to be among the most loyal and affiliating couples. So they choose a couple and they live together forever. So the same happens for stars. They tend to form binary systems. And let me give you this diagram. So here, these blue points are black holes with given masses that live together. What happens when they live together? Well, they get closer and closer and closer, and in the end, they merge, they collapse, they merge, and they form one single object. Okay, that is big. And for neutron stars, so if you have two neutron stars, they will start approaching each other, and at some point, they will merge for another object that break this black hole to this another object. Well, why am I telling you this? Because black holes, as I said, for named scientific, and this changed dramatically in 2015, where with the first observation of gravitational wave. When they orbit and approach each other, they emit huge amounts of gravitational waves. But of course, you need to be able to detect gravitational waves. And again, technologically, this was very, very challenging. You can go to the technical designs of these interferometers to see how amazing it is, what they are doing. But okay, they now are able to detect gravitational waves. And through these detections, now we can observe, if you want, but rather than observe, will be like listening to these objects. Okay. So this is a little exercise. So before 2015, we could only observe electromagnetic patterns. So we could only see light, frequencies, but light coming to us with our telescopes. So till then, this is how we could see the universe. Okay. Okay. So what was that? Yes. Sorry. Yes. So this is all we could see. Now, when you're looking on the screen, or when you are looking at those lights over there, you have missed. Okay. Now, if I think, let's see this one. So now with sound, you get much more information, right? So even if you were looking there, there will be an error. So that happened in after 2015, because now, for instance, we can have this amazing holistic observation, okay? And why I'm saying this? Because in the merge of two neutron stars, so this is something that was happening in the universe, but despite the impressive and spectacular event, so it emits a lot in electromagnetic waves. It's very easy to miss, because first of all, you may not be what happened? Put here some of these objects collapsing through gravitational waves. So when you put your telescopes, okay, look there, and tell you what you see. And that's what they did. And then they were able to detect this event both with gravitational waves, and not only that, but also with arithmetic waves. And this is amazing because, well, only this single one event, the cosmologists here can tell you, played a crucial role in our understanding of the universe as a whole, because it ruled out many scenarios that were thought viable and now are not. Okay. Not only that, also by studying the spectra in the arithmetic spectrum of this event, it was confirmed that some of the heavy elements like gold, platinum, this kind of things are formed in the collision of neutron stars, not in the interior of stars. So for those of you who are in the board, so you are going to observe that and you are every piece of a neutron star, which is something that should blow your mind. Okay, so what about the universe as a whole? So as I was saying at the beginning, observations and theoretical work and experiments and many things, we have a pretty good understanding of the evolution, the composition, and the structure of our universe. And we have managed to come up with this understanding of the entire universe just by observing from the Earth, this tiny rock, this solar system. To me, this is one of the milestones of human intellect, being able to get understanding the entire universe just by observing from us, because we cannot experiment with universes, okay? We cannot make experiments. We can simply observe what the universe is there to offer. So one of the things we learned is that actually most of the universe is made of dark matter and is so-called dark energy. And dark energy has a funny story, because I would say the it is called cosmological constant. It's just a number, okay, that we need to introduce in our. But I think that this is already by Einstein in his field equations, not to explain that the universe is expanding in accelerated ways. That's why we need dark energy, but because he wanted a closed and static universe. Then, when it was found that the universe actually expands, the cosmologists got rid of this cosmological constant. Then quantum mechanics was developed, and by the 60s, 70s, people understood quantum mechanics and how the fundamental laws, particles, and forces in nature can be described in terms of this quantum physics. And then, when applied to cosmology, they found this funny thing that this is matter that is essentially a cosmological constant that should be there. But if that constant was there, then the universe shouldn't exist as big as we see today, because that should expand the universe very quickly. Since should be very different from what we see now. So there was this problem that this should be there because it's a very natural thing to have in our understanding of the fundamental laws of nature. But it doesn't seem to explain observation. Until in 1998, they observed that actually the universe is expanding. So this is what these guys were predicting. The problem that we need the natural value issue. Okay, this is just a technical issue. It's not a fundamental. I mean, don't get me wrong, because nobody's here, but technically it's fine. The model works. Okay, there's no inconsistency in there. And finally, now, this makes that we live in an era of maximum access to information. And you might say that it's because we have internet and smartphones and all these things. No, it's because so since this dark energy started making the universe expand in a certain way very recently, the galaxies will, or the objects in the universe will expand from each other faster and faster and faster. And right now, actually, there will be a moment where we will not be able to access the information emitted by those objects. Okay. So that means that now we have to collect all the information you can because we live a few billion years from now. According to the understanding of the universe we have now, we will stop being able to collect any information at all. Okay? So telescopes will be useless, and interferometers and all these things will be all alone and without any chance of increasing our knowledge about the universe. Now, this depends crucially on the properties of this dark energy. I told you the most normal thing seems to be this possibility of constant, but the solutions like to try alternatives, and this will, as I said, this will depend on the properties of this dark energy. For instance, if it's not related to a constant, then the universe could recollapse, or instead of becoming this peaceful place where everything will be disconnected and nobody will be able to obtain information from any point of the universe, it could be much faster expansion, and then the expansion of the universe in the universe. So things, different things can happen, and it will depend on the properties of dark energy. Now, how can we understand or prove how the universe will evolve from now on? Well, one of the main pros is the formation of structure. This is a simulation of how dark matter collapses in the universe. And then, this is going too slow, but it's because of the connection. Well, the important thing is that you form all these structures, and galaxies will form where these structures form and all those things. So why am I showing you this? Because this will be by studying the distribution of matter in the universe, we will be able to grow this dark medium. Okay, these structures are going to form in the medium of dark energy. And now to give you an analogy of how this works, I will show you this picture, and this is a bottom of a beach of ocean, and then what you see here, some dunes, okay, that are formed by the currents or the tides of the sea. Okay, here you have exactly the same, but instead of being formed by the tides and currents of the sea, it will be like the wind blowing here. Okay, so by studying this structure here, then we can get information or understand the properties of the medium where these structures are being formed. So this is one of the key things or more important things that the cosmologists are doing. Next time, we'll try by the properties of this structure. In principle, we should be able to tell things about the medium where these structures are. Dark energy. Okay. So despite being dominated by this dark medium now, we have a red picture of it because luckily now there is a lot of activity in community and many experiments that will help us unveiling all these things. One, as I said, is the astronomy of gravitational waves. This will play a key role. Now there are 3 at least operative interferometers. Soon we will have 5. In principle, we will have some of space. Another one is the James Webb Spatial Telescope that has been launched and is already taking data. And this is a comparison of how far the Hubble telescope was able to see and how far we will see with the James Webb telescope. This is the same picture taken with both telescopes. So this will allow us to see much further objects and much further also. Then here, the matrix in the universe, we will have satellites like Euclid, but very important for this talk will be SKA, because this is something that you guys are developing. Okay, so this will be the, well, these are square kilometer array. So essentially it will be a square kilometer array of private telescope. Will be the biggest one in the world. And it will allow us to get much of the pictures of the universe and many other things that wouldn't be possible with that. So I think South Africans, you should feel very proud of this participating actively and leading this project. And I thank you for supporting this kind of research. And of course, there are many more experiments and satellites and things that are being carried out to try to understand where we live. And this is now the end of the talk. This reached the end. You enjoy it. And as I said, this will happen in very, very long time. So that's also the age. Okay, thank you.
Now, you explained that not to talk method is the method. How do you talk about?
It's about 25% of the universe. And organisms are the most robust evidence for that. Now we have better robust evidence for our history, description of galaxies, also with you can see collision of galaxies. And the images can only be explained. You assume that there is some dark matter. I'm going to get to technical. Essentially, yeah, now we have evidence from many different tools. And the good thing is that they both point towards the same amount of dark matter in the universe. So we can do the oh, sorry, this is well, I think the same applies. That's again, the cosmic metabolic background tells us that we need dark energy. The resonance of supernovae tells us that there should be dark energy. And the distribution of matter, so we have something else. And you can see how it distributes in the universe, and that tells you also Again, so all these independent probes conspire to give you this more or less the same amount of dark energy in the universe. And this will be 70%. Did I answer now? Um, trying to decide how problematic I should say here. But okay, I'm gonna be honest. This is being recorded, no? There shouldn't be that on it. So could be, okay? But the fact that could be doesn't mean that it's likely to be. But it is, I mean that this happens. Is able to predict those directions are also many others. So if you want to come up with a consensus for two competitors, don't look just at one observation. So you should try to explain at least the same amount of observations that you can model. And I would say no, you should come up with a sort of smoking time on that model too. So considering which are experimental relating to the model, good thing of the when our theories work is because they predict something that was not expected, and then the theoreticians that the experimentalists look there and you should see that. They look there and see that. And I think that's all. Yeah, from this is very difficult. So I think we can discuss that. So we can talk now if you want. This is very question. No?
If so, we have the
Yeah, so that's a very difficult problem. You have standards and specimens. So in the standard model, at least, there is a profile of dark matter. So it's pretty straight up. It's much bigger than the plane of the galaxy. And the density drops over the end. So in velocity, yes,
precisely because we are sensitive, we can measure the rotation cost, so we can measure the velocity of the stars, and that is a measurement, if you want, of the gravitational potential in the interior of the orbit. Okay, and that's why you need the dark matter. Did I answer? Yeah. Yeah. Yes, and people are trying to measure. So that depends on the precise model of dark matter, because since we don't really know what dark matter is, we don't know if yeah, you can measure the gravitational potential. But, so the gravitational potential, so yeah, that's what you measure. So for instance, if you measure lensing, you know lensing? Okay, so you measure lensing, then you can infer the gravitational potential that produces that lensing, and that gives you an idea of the dark matter that you have there. So yeah. Yes, exactly. For instance, there was this finding experiment, the Sama experiment, that was running in 2000, and they were trying to measure because of the Earth moves to the dark matter distribution. So they should see a linear variation of the detection of matter particles if they could detect them. And at some point they claim that they were seeing this variation in their detectors. Yeah, that's what I was going to say. Yeah, so this experiment is not, so it was only observed by them. It's not the idea, it was a true effect, or if it was an effect on matter. But groups have to be able to reproduce it. So they didn't have any. We have experiments to detect not only matter particles, but the products of dark matter particles annihilation. Because if they are related to the rays, for instance, and by studying the gamma rays and in space, cosmic rays, you could try to see if something anomalous is happening. And that will be dark matter. Also, for instance, now these groups are able to trace the orbits of the stars near the galactic center. So they could be sensitive to some gradients of density of the dark matter near the center. So some groups are trying to see if they can see some deviations in the orbits that could give you a hint of the dark matter distribution there. Okay. No. Well, when we do this, in principle, they form structures, we don't know the interactions as far as we see they behave as could be, so there are models of superficial transfer, this kind of thing, so that would be that. So there are some people like to speculate, so probably will find some models for whatever you want. It's called another article with a given mass that really interacts with anything. No, and I'll tell you why. And it's because of this phenomenon of the synthesis I told you about. Because within this phenomenon of the synthesis, from there we can compute or measure the abundance of all the matter in the universe. Even if you may think, okay, one of them is that was
would be gone. Because I will originate from the and we miss those measures. So if anything should be something used before the knowledge of this. So
Yeah. Speaking of this, extremely we've got plenty of database. We will complete model and start again. What is the most likely fate of the universe and volume according to those data papers that we did go? Is the universe going to expand further? Is it going to accelerate more? Is it going to collapse? What is the most likely fate? So can we sleep safe tonight?
Yeah, I think that's so. Personal opinion is that the standard model works. In the standard model, both for cosmology and elementary particles, we have a very natural candidate for dark energy, and that is the cosmological constant. So for me, the accelerated expansion is introduced by this cosmological constant, and that means that unless something new is discovered, so as of today, I would say we are doomed to end up in a de Sitter space. So things will, the universe will expand exponentially, will enter another phase of inflation. Maybe after that, there is another universe being born or something like that. But I think that's, but of course, I'm a Bayesian believer. So if I get new data, I will update my beliefs.